We've learned a lot about calculating derivatives given a function, but sometimes you actually want to go the other way. Sometimes you want to start with a function and instead of calculating its derivative, find a function whose derivative is the one that you started with. Here's an example. If we have an object that moves back and forth along a line, suppose that we know that its velocity function is v of t equals 4t plus 3 meters per second. Could we find a position function for this object? Well, the reason that this is, instead of finding a derivative, it's sort of going backwards, is because we know that the derivative of the position function is the velocity function, right? And we know if we have the position function, we can find the velocity function just by taking its derivative. But in this situation, we know the velocity function, and we want to undo the derivative to get s, the function s of t. So instead of calculating a derivative forward, we're kind of calculating a derivative backwards, or undoing a derivative. In this particular example, this is something that we can do basically just by guesswork. I mean, we have so much experience calculating derivatives that we can kind of imagine or intuit where or what function would produce this as its derivative. So the 4t part, right, we know that a derivative, from the power rule, a derivative will decrease the exponent by 1. So if you undo a derivative, that should, sorry, that's backwards. If we do a derivative, the power rule decreases the power on t by 1. And so undoing a derivative should increase the power on t by 1. So if this 4t part is the derivative of something, it should have come from something that looks like t squared. But, you know, the derivative of t squared isn't 4t, it's 2t. And so we need an extra factor of 2, just so that if we take the derivative of 2t, we end up at 2t squared, we end up with 4t. And then we can reason about this 3 term the same way. So what is 3 the derivative of? Well, it's the derivative of 3t. So here's a function that might be our position function, right? We have successfully undone the derivative because, right, we can check our work, because if we now do the derivative forwards instead of backwards, we get, let's see, power rule makes this 2 come down, we get 4t plus 3, and sure enough, that is the velocity function that we started with. So this formula for our position function is working, right? Its derivative is the velocity function that we started with. But actually things aren't so simple, because this isn't the only position function that would work. Another option for what the position function might be is, well, we know that this 2t squared has to be there because the derivative of 2t squared is 4t. So we need a 2t squared. By the same token, we need a 3t term so that when we take a derivative we get 3. But we could add anything here as long as its derivative is 0. Well, what kind of functions have a derivative of 0? Constants do. So we could have a plus 1 right here. Or another option would be 2t squared plus 3t plus, say, 2, or 3, or 5, or 100. Right? There's any constant could go right here. And we would still have a position function whose derivative is this velocity function that we started with. So there's not one way to undo a derivative. In fact, there are always going to be infinitely many ways. If you have any function whose derivative is this velocity function, you can add a constant to it. So this problem of undoing a derivative is actually going to be a little tricky, because there's never just one answer. In fact, there's always infinitely many answers. So this process of undoing a derivative, first of all, let's give it its name. It's called an antiderivative, which makes sense. Anti is just the opposite. If we want an antiderivative of a function f of x, we'll call that capital F of x. And what we mean by antiderivative is just some function whose derivative is the function that you started with. And what we noted a second ago is that if you have some antiderivative, you can add any constant to it, and this will also produce an antiderivative. So because you can choose any constant right here, there are always infinitely many antiderivatives for any function that you start with, little f of x. Sometimes you'll see a different notation for antiderivative. Sometimes you'll see this clump of symbols to mean an antiderivative for little f. This is called an indefinite integral, and that terminology at this point is sort of unmotivated. Why this word integral and what makes it indefinite? And I'm going to leave that vague for now. You'll learn in future calculus classes what exactly this terminology means. But just keep in mind that this clump of symbols with this this is supposed to be a very long S for historical reasons. This clump of symbols really just means the antiderivative of whatever function is showing up inside here. So our previous example with this velocity function was the antiderivative of 4t plus 3 dx. And what we found was it's 2t squared plus 3t plus any constant, right? We can have any constant here, and so to indicate that we can have any constant here, I'll just write capital C. And we'll just keep in mind that capital C, it's not a variable really, it's a constant, but it could be any constant. So let's look at a couple examples of finding antiderivatives. Now, really, we don't really have any way to calculate antiderivatives or indefinite integrals, except for the fact that we have so much experience differentiating things that we'll often, and usually, at least for now, be able to guess antiderivatives. So for example, let's find antiderivatives for this function, sine of x. In other words, we're going to be calculating this indefinite integral of sine of x, or we might name it capital F of x, so however you want to write it. So we just want to write down some function whose derivative is sine of x. Well, it's going to be something involving cosine of x. One nice thing about guessing antiderivatives is you can always check if your guess is correct by taking the derivative of this function and seeing if it's right. If we take the derivative of cosine, do we get sine? Well, no, the derivative of cosine is negative sine, so we need an extra minus sign out in front. So now when we take the derivative of negative cosine, we get negative sine, which is just sine. But remember, you always have an arbitrary constant at the end, because if you start with any antiderivative, adding a constant gives you another antiderivative. For a second example, let's find the antiderivatives of this function. G of x is 1 over x cubed. So 1 over x cubed, that's x to the minus third. Now we can kind of, use our understanding of the power rule. A derivative would decrease this power to minus 4, so an antiderivative should be the opposite. Instead of decreasing the power by 1, it should increase the power by 1. So it seems like we should end up with something like x to the minus second. But if we check this by taking the derivative of x to the minus second, what we get is minus 2x to the minus third. Well, that gets the x to the minus third part right, but we don't want this minus 2 out here. So we need some constant multiple in front of our x to the minus second, waiting to cancel this minus 2 that would come down when we differentiate. So what would cancel minus 2 and just produce a 1? Well, that would be minus a half. So we need a minus 1/2 right there, and of course always plus a constant. All right, and if you wanted to rewrite this, you could write this as 1 over 2x squared plus c. Okay, and then remember, you can always double check this by differentiating. The derivative of minus 1/2 x squared is minus 1/2 times, and then the power rule, minus 2x to the minus third, and then the constant term, its derivative is 0. And sure enough, these cancel like we planned, and we get x to the minus third. And so this verifies that our guess for the antiderivative is correct this time. For one other example, let's check, is this function, x sine of x minus cosine of x plus 3, an antiderivative of this function, x cosine x? Well, we can check just by, if capital H is an antiderivative for lowercase h, then that would mean, so if so, that would mean that the derivative of capital H is equal to little h. Well, we can calculate the derivative of capital H, so let's do that. For the derivative of capital H, for the derivative of this first part, we're going to need to do the product rule. So let's see, derivative of x is 1 times sine of x plus, and then x times the derivative of sine of x is cosine of x, minus the derivative of cosine of x, which is minus sine, plus the derivative of 3, which is 0. Okay, so, well, it looks like things were looking good at first because we got this x cosine x part, but we ended at these signs, instead of canceling, in fact, since they're both positive, they add to each other, and we get 2 sine x plus x cosine x. And this is not little h. So the answer to this question is no, right? Because the derivative of capital H is not equal to little h. On the other hand, we can see how we could fix this. If we just change this minus sign to a plus, then that would leave this minus sign alone, and then this sign we'd be adding a sine of x to a minus sine of x. So in fact, right, the antiderivative of little h is, it's not x sine x minus cosine x plus 3, it's x sine x plus cosine x plus 3. Or really plus any constant. Okay. For a final example, let's check, is this function, natural log absolute value of x, an antiderivative of this function, 1 over x? Well, it seems plausible at least, because we know that the derivative with respect to x of natural log x is 1 over x, but this is actually true only for positive x values, and that's because the domain of natural log of x is just positive x values. So this question is, the answer to this question is not clear, because the absolute value of x here sort of changes the domain, right? The domain of M is any number that isn't 0. And we haven't checked yet what the derivative of this function is, so let's do that. So to check if capital M is an antiderivative for little m, we can just take the derivative of capital M and see, right, do whatever calculation we have to do, and see at the end, do we get little m? All right, so let's differentiate with respect to x the function natural log absolute value of x. And we have to use the chain rule here because we have a natural log with some other function inside of it. So the derivative of natural log is 1 over, and then put the inside function in here, and then multiply by the derivative of the inside function, so derivative of absolute value x. And we have calculated the derivative of the absolute value of x. The derivative of absolute value of x is x over absolute value of x. All right, but now we should simplify this. So this is x over absolute value of x squared. But if this denominator is squared, right, the absolute value of x squared and x squared are the same thing, right? The absolute value throws away the minus sign, but the minus sign is going to get thrown away anyway because there's a squared here. So this absolute value of x squared is the same thing as x squared. But now we can simplify this because x over x squared is 1 over x. But that is little m. So this time, the answer to this question, unlike the last example, the answer to the question is yes. This function, natural log absolute value of x, is an antiderivative of 1 over x.